Okay, so now we've established where this equation comes from in a very rigorous way, and it combines the concepts of potential energy and this shape here without me just saying, oh, well, it's this teacup potential. Now, for the purpose of a lab, like 2100 or 1100 lab, we don't need all that background there. We can just say, look, a spring has a force like this, and because of this negative sign, if I set the two equal and then I bring it over, I end up with a positive sign like this. And this is cool because this is not a hard problem to solve. Or, well, what else could we say? Yeah, and we can then show the solutions, and then after the fact, you sort of show this teacup potential here, and I'll reiterate that in a little while. Okay, so let's go and do some basic. This is some really simple. It's called what is this? Second order linear. Excuse me, it's really heavy duty. Second order, meaning, excuse me, second derivative of time, linear. Excuse me, the hiccups all of a sudden. I didn't eat my dinner that fast. Maybe I'm drinking these beers too fast. Second order linear differential equations. We call them diffie-Q. And that's what this is an example of. Oh, this is a homogeneous one, too. I know. It's lots and lots of symbols, man. Tell you what, you send this home to your parents and you go, wow, look at all this stuff I'm learning. Send me some money, please. So anyways, it just means that I have the second order with respect to time plus the original equation, and if I add them together, that equals 0. And it could be negative, but in this case, it's positive. So this means that we have a possibility of a very simple formula of function that could take a place of x. Now, remember earlier that we required that x dot is not 0, or it's not 0 in general, meaning it's not 0 all the time. So that means that whatever function we come up with has to have a time dependence built into it. So in general, something like this equation here, even if it's not time derivative, if we have a function and we take the second derivative of it, or the delta x delta t, and some constant times the original function, it equals 0, the general solution to that is cosine of x. And so to simple approximation then, if I say cosine of x is my solution, then the first derivative is negative sine of x. And then the second, if I take this derivative of sine, which is the second derivative of cos, I get negative cos of x. So if I plug it into here, you notice that the second derivative is negative cos of x, and then I have cos of x, and then b just equals 1. And notice when I add them together, it equals 0. So this is a very simple, basic second order linear differential equation. It's got a huge name. It sounds super scary. But at the end of the day, it's a pretty tame beast. And it's because of the plus sign and because of the 0. And after that, if that's negative and that's not 0, it gets to be ridiculously difficult at times, and it takes at least a semester just to learn the beginning basics of it. But since most times we know about forces, and remember F equals ma, and A is x double dot, right? You could see where this could be pretty useful. Now, since we realize that whatever function that we're going to put in for x has to have a time dependence, the easiest way to do that is within the argument. They call it the argument of cos. Whatever is inside the parentheses, instead of having it be some constant, we're going to have it be some constant times the time. So in other words, we're defining a time dependence, x of t equals to some constant times t. We want to keep it really simple. Now, be very careful. X of t is not equal to x dot. Those are two different beasts. Just because I know x of t doesn't mean I know the speed. The x dot is the time derivative of x of t, the first time derivative, or the first delta x over delta t. So anyways, if now we say that we want to find out that now that x is equal cosine of c times time, so there's a time dependence inside cos, that means that if I want to know what is the change in cos over a time interval, I have to do the chain rule again because there's a time dependence inside the parentheses. So that means that I first take the derivative of cosine itself, and then I multiply it times the change of the inside over t. So this one is pretty easy. It's just c. The change of cos is a function of time, is just sine, as we showed before, and it's negative sine. And then if we hit it again with the same chain rule, we get c squared times cos. That's great. Nice. So one thing we notice is that the b we slapped on up here is equal to c squared. So if we end up with minus c squared cosine of ct. If we make b equals to c squared, then this becomes 0. That's cool. And then because we know cosine is of angles, and the generalized form is radians, we then say, oh, well, we're going to call c omega the number of radians per second, so it's sort of an angular speed, a rotational speed. And then omega times t is radians per second times seconds, so we end up with radians, and that's great because we want whatever's in these parentheses to be equal to radians, so that cosine of it makes sense. So great, we're on our way home. So then we say, okay, we're going to make this is remember, this is the equation we set up using either energy or force, and we want it to look like this because we want to shoehorn it, this, like we have this square peg and we want to put it in a round hole. So we have this whole technique to get the right answer for this equation. So we have to take our equation and make it look the same. So we just divide by m. So we multiply by 1 over m to get x double dot k over m times x. So now we know that k, this implies to us that says, oh, so k over m must be equal to b, which is also equal to omega squared. Right? I forgot to say that here, since b is equal to c squared and c is equal to omega. That means that c squared, omega squared equals to b. So that tells us that omega equals the square root of k over m. Now there's some other heaviness built into this that we don't deal with, but we define k as the wave number, and it's equal to 2 pi over lambda. We don't need that for the 1100 lab or the 2100 class, so don't worry about it. But it's so interesting to me that it's all tied together, right? There's circles and sine waves and cosine waves everywhere in Mother Nature. So we see that we're going to have x is equal to cosine omega t, and we're going to throw in this a as well, but I'll get to that in a minute. But if we were to plot this, we would see this sort of, well, this is a sine wave because it's 0 at x equals 0, but cosine, sine, they're basically the same thing. So we define a cycle as if we start here, a cycle is where the thing repeats. So you could start here and go here, etc., etc. And we say, and remember, see, this is the time axis. This is the x-coordinate. And so we define the time for one cycle as capital T, and we call that the period. And since it's a second per cycle, if we take the inverse, we get cycles per second. So how many times in a second does something repeat? Remember, we need to use this when we're having our pendulum, our spring and our mass, and it's going up and down, right? We can't. What we do is that we're going to measure a time, but we're counting cycles, and then we get a number of seconds, and then we can figure out what is the frequency and then take the inverse. Well, what we do, of course, is we just take t and divide by the number of cycles. But I just wanted you to see how they tie together. Now, we add in this a because that's called the amplitude. And the reason we have to do that is because if we don't, then that means that anytime we have a spring, a weight going up and down, any kind of harmonic oscillator, we're telling the world that it can only go up and down to +1 and -1. And we know that's not true, right? It doesn't make any sense. So we have to add this a term. Now, we also know that we have, and then here's the big time key right here, omega. So omega is radians per second, right? So it has to do with how many, when a circular object is going around and round, of course its positive direction is counterclockwise. And so we know this is radians per second. So that's how fast something is going around. So how do we relate that to the things that we measure? Because we don't have a way to measure omega, but we can measure cycles per second and we can measure seconds per cycle. Well, there is just this simple definition that omega equals 2 pi f, right? So how do we evaluate that? So it's cycles per second frequency. And remember, 2 pi is equal to 1 circle. And so we have circles per cycle. So then it ends up being so circles per second, see? Because 2 pi is 1 circle. So omega is the number of circles per second. And then using our other definition for frequency, we can also say that omega is 2 pi over t. And so that's circles per second, circles per cycle, and then seconds per cycle. But when you have to bring it up to the top, it once again becomes cycles per second, and we get the same answer. But we can then, invert it to get period, and we see 2 pi over omega. But we keep in mind that omega is equal to the square root of k over m. Isn't this neat the way it all ties up, right? It's because we have this differential equation here sets the conditions for the solution function, but this equation was also dictated by conservation of energy, and it was dictated by the force equations. And so all these things, it sort of like funnels us into the right answer. And because we needed to satisfy this differential equation, we ended up with this definition. And we noticed then that the period can be affected by the mass, and it can be affected by the spring constant. And one thing we could have done, I suppose, is use different springs. But at the end of the day, then, we have our function a times cosine omega t. And so we know that omega equals the square root of k over m. Let's make sure I got that right. And we know that omega is also equal to 2 pi over the period. So we see that period equals 2 pi over the square root of k over m, which is the same thing as m over k square root 2 pi. So we notice then that if first of all, we have a spring. And in principle, our spring, number one, should satisfy f equals negative kx. So we used a hanging spring because with the hanging spring, the force we apply is mg. And in principle, if the spring has to satisfy this equation here. First, if it doesn't satisfy f equals negative kx, then it can't. All the rest of the things we just went through don't apply. So what we've done is we put a variety of weights on, and so that's why that's the x-axis. And then it's unfortunate. That's why it's the horizontal axis. And on this axis, we're going to have the x, the stretch. That's why we set that all up. I'm not going to get into that as in a procedural question. But remember now, let's think about this. So that means that this is what the spring is going to do. But for us, it becomes f equals kx because this is the force that we're applying to it, not the force that the spring is giving us. So this is the force we're applying to it. So we would expect then that x is going to equal 1 over k times whatever the force is. That this is what we observe, the things we measure. So then we take several points of different masses and we do a straight line fit. So what we want to see then is the r squared is equal to about 1. And if that's true, that means that this rule is, this spring obeys that. And remember, we made sure that all the coils, every single coil is open slightly, but that's procedure. We're doing background right now. So that means that, first of all, that we have a spring in front of us. It does indeed obey this rule. So if it obeys this rule, then the spring should also obey this rule. So we don't have a way of testing K, but we can measure the T, and we can also examine whether A has an effect on T. And our equation tells us that amplitude A should have no effect because it's not part of this equation. Now, because we always want to do straight line fits, we decide that we're going to square this. T squared equals m over k times 4 pi squared. And in this case, once again, we're taking masses, but it's not being converted into force, notice. And if we plot t squared here, so that means that t squared should equal 4 pi squared over k times m. And then there's that effective mass, and I still haven't come up with some simple explanation that, I mean, it's in the lab manual, but since I haven't explained it to you, our general rule is I don't hold you responsible for it. But anyways, if I do a t measurement, a period measurement, and square it, then if I plot mass and t squared as a function of mass, I can once again do a straight line fit. And I should notice that this slope is 4 pi squared. Well, I don't notice it. My equation tells me that. So then if the slope equals 4 pi squared over k, I can invert that once again and say 4 pi squared over that slope, the number we get should equal to k. And it should match the k from earlier. Now we're going to notice that the y-intercept is not equal to 0. And if you look at the way I set up the spreadsheet, I allow, this is where it's super important to let the y-intercept, don't force the y-intercept to be 0, but we've never done that before. But anyways, this is now the background and the reasoning for it. For the lab itself, it's basically starts here with this on the left, then it goes to this, which is not done as well, really well in the lab manual, excuse me, it will be when I rewrite it. And then we have our definitions, and once we tie it all together, then that means that we expect t to depend on k and m and not on amplitude. But first of all, we have to make sure that our spring itself obeys this proposed spring law. Okay, that's it. See you soon.